Hello, everyone. Hope you're doing well. Let's keep talking a bit more about operators as we get into our final week. We have two things that we want to talk about in this series of video lectures for week 10. The first one is going to be talking a little bit more about operators, because when we talk a little bit in linear algebra about what all matrices can do, we talk a little bit more than just, oh, they give us certain vectors and help us map them to other vectors. We also talk about how matrices interact with each other. You may remember the concept of an inverse matrix, for example. An inverse matrix of a matrix A, and let's say that A goes from Rn to Rm, so that this is an M by N matrix, only existed whenever you were looking at a matrix that was for a space where the matrices were square, in which case you'd be looking for where M is equal to N. So this inverse matrix of A does not exist if M is not equal to N, because we would say such a matrix was not square. We could not get a nice inverse matrix from that. Kind of a reason why you might be able to say something like this is take a look at your spaces here. An inverse matrix would have to be mapping any element inside of Rn to a unique element inside of Rm, and every element Rm would have to be covered by an element in Rn, and that's just simply a little bit tricky to do with a linear map unless you are looking at a space where the number of basis elements you have in Rn is equal to the number of basis elements you have in Rm. In fact, it's impossible to do unless you're looking at a space where if n is equal to m. Then we could go through and define an inverse matrix in the following way. There are a few ways that we went through and did it. In one case, when n was equal to 2, we would define the inverse matrix to have a specific formula, which was 1 over the determinant of that matrix. And if we said that this matrix was of the form A, B, C, D, then this is times the matrix D, negative C, negative B, negative B, negative C, my bad, negative B, negative C, and A. And the way that this inverse matrix operated was that if you multiplied the matrix A on either side by the matrix A inverse, just one side at a time, so like A inverse A or A times A inverse, then what you would get back is a special type of matrix known as the identity matrix. So for example, if I was looking at 1, 2, 3, 4, I could go through and use this formula to figure out that the inverse of this would be something like this. You'd have 2, 1/2, 1, and 3/2 right here. I have negatives right over on these sides. So this is an example of what a inverse matrix might look like. If you multiply the matrix 1, 2, 3, 4 by this matrix, which we recall is you take a row and you take a column and you consider those both two vectors and you take their dot product. The dot product of 1 times negative 2 plus 2 times 3/2 gives us 1. So I'll write that down here. Get 1 for the top left corner since I took the top row and left column of these matrices. Then I could do the same thing for top row, right column, multiply those rows and columns together and get something that equals 0. That is 1 times 1 plus 2 times negative 1/2, so that's 1 minus 1. Then I could do the same thing for the bottom row and left column, which is going to give me the bottom row left column of this entry in the matrix, and that should give me something like 0 once again. And then finally, going bottom row and right column, I could get something like 1 from this. And this was an example of what is known as the identity matrix. Sometimes we would call it I2 to signify that this is the identity matrix that is 2 rows and 2 columns. And the neat thing about this identity matrix is that it acts a lot like the number 1 acts in the real numbers. The number 1 acts like, well, if you multiply anything times 1, you get itself. And the exact same thing is true with this matrix. You can check yourself and see that if you take any matrix A and multiply it times this particular matrix 1, 0, 0, 1, then what you end up getting is exactly that matrix back. So that's a quick review of what we would do in the 2 by 2 case. Now, we also had a way to find inverses in terms of any sort of dimension. So, for example, if n was equal to anything, so n arbitrary, then there are a few ways that we could go through and do it. Some of you may be familiar with the notion of like something like a cofactor matrix, which is a way to use determinants to figure out what this inverse would be. And some of you may be familiar with a notion called Gauss-Jordan elimination, which is that you start with the matrix A, n by n, as on the left side of an augmented matrix, where the identity matrix of the appropriate size is given in the right-hand part. So for example, maybe you start with 1, 2, 3, 4, 5, 6, 7, 8, 9, and then you have the corresponding identity matrix at the very end here. So the little bar is telling us that we are augmented the matrix. The thing on the left is the matrix A that we want to invert, and the matrix I on the right is what we're starting with. And our goal was to use elementary row operations to get the left-hand side to look like the identity matrix. And once we've done that, the thing on the right-hand side would become A inverse. The identity on the left, A inverse on the right. The augment now would be of A inverse after we've gone through these elementary row operations. Now, here's the interesting thing about using either one of these techniques is that at some point, sometimes you either get, you might be getting something that is impossible to complete. In fact, this matrix right here, 1, 2, 3, 4, 5, 6, 7, 8, 9, does not have an inverse. If I went through and attempted to complete all of the row operations to get this matrix A to look like the identity matrix on the left-hand side, I would be unable to complete it because no matter what row operations that I would get, I would always get a row full of zeros, also sometimes just called a zero row, in that matrix, which that's not what the identity matrix looks like. It's got to have a 1 in every row instead. So no matter what row operations I would do, I would always fall short. And there was a notion as to why this matrix was not invertible that we explained briefly, which is that the determinant of this matrix is 0. In geometric terms, what we mean by that is that if you take the vectors 1, 4, 7, 2, 5, 8, these are the vectors that span the column space of this matrix, then these three vectors do not span all of R3. These three vectors are not a basis for the space of R3. If we consider the volume of the region that these three vectors would generate, we'd be looking at a plane that has volume of 0. The determinant was exactly that volume that these three vectors would generate. So this sort of thing tells us maybe we aren't actually getting a thing that is invertible, because what we're doing is as we send a matrix through, send a vector through this matrix, all possible vectors that could be mapped through this matrix are only getting mapped to a plane. This does not seem like an invertible action. It's not an action that you could do to get something that is inside of a plane like R2 and get it to map to everything inside of R3. Those are some of the concepts summarizing what we discussed back in either 632 or 689, depending on where you saw linear algebra last. So that's this sort of review of what we want to start generalizing in terms of looking at inverse operators. Because we've worked with matrices in linear algebra and we have some of that notion, but we've also seen that operators are general versions of these sorts of matrices. You can have two metric spaces, perhaps, or two normed vector spaces, perhaps infinite dimensional like U and V, and you can define a linear operator between the two of them. Now, just like before, we're going to want to stick to bounded linear operators, which we recall means that the operator has the operator norm on it, and that operator norm is finite. So that's what we mean when we write an operator in this particular week. We are going to you'll see me use a lot of this notion of it being a bounded linear operator so that our things can be nice and continuous and work neatly with the type of mathematics that we want to do. Essentially, we want to start thinking about these bounded linear operators as like an extension of what we were learning about with matrices. Just like how we were talking about an inverse matrix existing, we want to ask the question, does an inverse operator exist? Thinking of it in the sense of functions, this would be like asking, is there a T inverse that takes me from one normed vector space back to the other one, such that whenever I consider the composition of these two maps, either T inverse composed with T or T composed with T inverse, that I get back to some sort of identity map. And that's what we'll be talking about in our section of the video today. So why don't we go ahead and start getting a few definitions down to start formalizing what this extension looks like from the world of matrices into the world of infinite dimensional world. Now, I think this is one that maybe is not in our textbook, but I do see this one come around a lot whenever we're discussing spaces of operators, because we talked about a Banach space as a version of a complete normed vector space. And an important extension of that is that if you have a Banach space that has multiplication defined on it, then what you're looking at is a Banach algebra. An algebra meaning that there's a way to multiply inside of the space. We talked a little bit about algebras for functions back in week 7 when we were working on the Stone-Weierstrass theorem. And remember that the important thing about an algebra is not only is it closed under vector addition and scalar multiplication, but it also has vector multiplication defined on it. And in this case, our vectors are these operators. Here's an example of a space that is not a Banach algebra. That would be the space of m by n matrices where m is not equal to n. If I have a matrix of the form 1, 2, 3, 4, 5, 6, and I have another matrix 7, 8, 9, 0, 1, 2, then there's not a well-defined way, at least in terms of matrix multiplication, for me to multiply these two matrices together. Typically, the way that we multiply is that it requires that the number of rows in the first matrix we multiply is equal to the number of columns. Switch that. The number of columns in the first matrix we multiply is equal to the number of rows in the second matrix that we multiply. And that's so that we could actually take a dot product for each row and each column of this matrix. For example, I can't take a dot product between these two vectors. So this is an example of something in which I cannot multiply. This means that the space of 2 by 3 matrices is not a Banach algebra. It is an example of something where the vectors that lie within, in which case the vectors are matrices, are not themselves multipliable. You can't go through and multiply them. So a Banach algebra is a complete vector space, which is also an algebra. And we also ask for one last property. We've already shown that this works for matrices, and in fact, we've also shown that this works for spaces of operators. It's the submultiplicativity property. So this should be an I right here. The submultiplicativity operator says that if you take the operator norm of two elements composed with each other, then in fact, that norm of the composition is less than or equal to the product of the norms of the two individual functions being multiplied together. We've done this with matrices before, and we talked about why this was true. It has to do with the supremum of the vectors that we are plugging in order to figure out what these norms should be. So if you want to see where we saw about that with matrices, take a look back at the video lecture 8-3 for the example that we did with regards to submultiplicativity. So here, the multiplication of operators is implemented by composition. We'll see that in an example here in just a little bit. But when I write AB times the vector x, the thing that I am implying is that I am taking the vector x and multiplying it on the left by the matrix B. Perhaps the way that this works is that I have 1, 2, 3, 4, and I multiply times the vector 5, 6. Once I go through and multiply this 2 by 2 matrix by this 2 by 1 vector, what I am left with is a 2 by 1 vector once again. It's like 1739. Here I'm implying that these are two numbers that are just right next to each other. It's not 1739. It is 1739. Maybe I could even write them closer to make that a little bit easier to make sense of. There we go. So there is the vector bx. But then after I get that vector, I then multiply the resulting vector that I would get from b times x times the matrix A. So if I had another matrix like 5, 6, 7, 8 right over here, then I would take that and multiply it times the resulting vector. Of course, that is telling us that there is an order of operations that's going on here. But the neat thing about matrices, and indeed about operators as well, is that this whole process is associative. Associative, recall, means that if I have parentheses around b times x, I could have also just multiplied the matrices a times b before I even multiplied times the vector x. Multiplying a times b would get me a new matrix, and then I could multiply that matrix times the vector x. The order in which that I operate is not important. So if I go through and then multiply this out, I would get another vector, which I could go through and calculate to give me another vector, which would be my answer for what it does it mean to take A, B, X. Now, some operators are very nice because looking at this implementation by composition, some operators act like they aren't even there. And those types of operators are called unit operators. These operators map every vector of a vector space to itself. In fact, you'll see throughout here that I had to change some of my notation here for what the unit operator was, because this is also a way that I see the unit operator being written. It's just like it's the number one. Now, I'm going to use the letter capital I instead, as I think that's more evocative of what this means in terms of our linear algebra courses, which is that an identity matrix is just any matrix or vector that you multiply times the matrix I just gets you one, or gets you that vector or matrix itself. And the way that you form a identity matrix is that you put zeros in the corners and ones along the diagonals. So you get a matrix that looks like this. Here you would have n rows and n columns. So these are in particular unit operators. Remember our notation from before that go from one vector space back to itself, like L of V. So that's an example of a unital Banach algebra then. The space of matrices, n by n matrices, is a unital Banach algebra because there exists a unit. The property of the unit is that it has a norm equal to 1, and whenever you multiply any other element inside of the Banach algebra times it, then you get back the element you started with. So an example of something that is a unital Banach algebra is that of the space of m by m matrices. That gives us a unital Banach algebra. But we can apply this sort of process to any sort of space. Let's take a look at the space little L infinity, for example. This is a Banach algebra as well. The space little L infinity, recall, is the space of all bounded sequences of real numbers, and we give it the norm, which is given by the norm of a specific sequence x of n in terms of the L infinity norm is defined to be the supremum of the absolute value of each of these x of n. So it is basically telling us this is the least upper bound that you could define for this sequence that you're working with. That should always exist because little L infinity is defined as the space of bounded sequences. But if you take two bounded sequences and if you multiply them coordinate by coordinate, like if you had the sequence 1, 2, 3, 4, and you multiplied it times the sequence 5, 6, 7, 8, so that the coordinates came together and multiplied coordinate-wise, then what you would get is a way to multiply two bounded sequences together. And what's more, the sequences that you get in norm, if you have two bounded sequences to start out with, if you multiplied those two sequences and took their norm, that would also be a bounded sequence. And in fact, you could show that it satisfies the submultiplicativity property. What we are saying here is that if you take the supremum over all natural numbers of the absolute value of xn, yn, like what you have right over here, then that's going to be less than or equal to the supremum over all m in the natural numbers of the absolute value of xm times the supremum over all n in n of y sub n. Notice how these two sides actually feel like they do fit. If we're getting used to this notion of supremum, then we notice that what's happening is we're taking a product and then taking supremums. And here we're taking supremums of each side and then taking a product. We've seen in some examples throughout this class before that what happens here is that this becomes a less than or equal to sign because these two supremums that we're finding, these two suprema, these are both least upper bounds for the x sequence and the y sequence individually, which when multiplied together are going to be, at least logically, potentially larger than the possible upper bound of the products of the two sequences put together. Essentially what I'm saying is, if you looked at these two sequences and took their least upper bound, then where their least upper bounds might be bigger than the least upper bound of this sequence when you multiply them together. So the order of the process is different, whether you take supremums first and then take the product, or whether you take the product of the sequences and then take their supremum. Think here I'm taking least upper bounds twice. Here I'm only taking it once. So that's our process for using this, this sort of idea. This ends up giving something that is a Banach algebra. An example of this sequence that works as a unit inside of the Banach algebra is something that would multiply times any sequence inside of little L infinity and give us something that just gives us that sequence back. And that sequence here does exist. That's the sequence 1, 1, 1, 1, 1, so on and so forth. Because if I took any of these matrices or any of these sequences here, and I multiplied it times the bounded sequence 1, 1, 1, 1. Multiplying these two together just gives me the exact same sequence, since we're just multiplying coordinate by coordinate. That's the example of the identity here. If I was going to go through and call this something, I would call it capital I for the space of little L infinity. So this is an example of a unital Banach algebra. It has all of the properties that we would need. Let's keep going a little bit to see an example of a Banach algebra that does not have a unit. And we actually don't have to go very far. Little L infinity has a closed subspace we've talked about before, which is that of C0. Remember that C0 is the space of all bounded sequences that converge to 0. So sequences that converge to 0. And this is a closed subspace of little L infinity. It has also the property that if you take two sequences that converge to 0, then the product of those two sequences must also converge to 0. So that gives us something that is a Banach algebra as well, as it goes through and satisfies this exact same property. However, C0 does not have a unit. Think, what sequence would I have to multiply a sequence that converges to 0 by in order to get exactly the same sequence back? Well, that sequence would have to look a lot like the same sequence that we had for little L infinity. In order to make these sequences multiply together coordinate-wise to get exactly the same sequence back, for this to be a unit, it has to have 1 in every single coordinate. The issue is this: although this unit exists in little L infinity, it does not exist in C0 because this sequence does not converge to 0. So whatever unit we might have actually doesn't exist inside of this space. This is an example of a Banach algebra that does not have a unit to it because the unit that it would have to have cannot exist inside of this space. This cannot exist inside of C0 because it does not converge to 0. So that is an example of a non-unital space. We could do the same thing for spaces of bounded or bounded and continuous functions on a metric space. So if, for example, we're in a space where X is compact, then we could define a space of bounded continuous functions on that space by just looking at all of those which are continuous. And then we could ask, okay, well, can we take two bounded continuous functions and multiply them together and still get a bounded continuous functions? Definitely for the bounded, because it's the same sort of story for sequences. You just take whatever their highest points could be, and either they multiply together and get the supremum, or the supremum is going to be lower than that point. So that does indeed work. Same thing for bounded functions in that same way. And then also back to the space of continuous functions, if you multiply two continuous functions together, you still get something that is continuous. So those are examples of Banach algebras. In fact, both of these would be unital because the unit function, which is the function which is just 1 everywhere, is indeed a continuous and bounded function of norm 1. Let's go ahead and start working a little bit with some of these operations, looking at this problem right here. Assume that V is a norm space and that C as an operator going from this norm space to itself is a bounded linear operator. Let's show that the norm of C raised to the power of n is equal to the norm of C to the nth power. So let's talk a little bit about first, what is C to the n? C to the n is C times C times C times dot 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 times C n times. But remember what multiplying an operator times itself means in this context. It means that we are composing C with itself that many times. So if we have something like C times C times C times C, and so on and so forth, this means that when you plug something in like C to the n times a vector x, that means you're going to first plug the vector x into C once, and then you're going to have n minus 1 times to do it after you finish that. You are just taking C of X and then taking that Y value you would get and plugging it into C once again. You may have seen this operation before where you take a look at something like 2, 0, 0, 1, and you map through the vector 1, comma 2. And you could see what this does to a vector. It will take the first component and it will multiply it times 2. But if you did this 4 times, if you mapped it through a matrix 4 times, then what that would do is it would take and raise this to be 2 to the 4th power instead. There's a process that typically ends up happening when you take the same operator and map a vector through it n times. And so sometimes there's a formula that comes from that. We talked about in our 632 or 689 class that there is a way for you to diagonalize a matrix and make calculations like these a lot simpler to work through. But let's talk a little bit about how norms operate with regards to these sorts of powers, like is given here in our question. I paused the video for a second because I looked at it and I thought I saw a counterexample to this problem as written, and indeed there certainly is. This should be just a less than or equal to sign. It is not necessarily true that this would be equal at all, and it may end up being an interesting problem or one that you talked a little bit about in your homework back taking a look at homework 9 with one of those questions about finding the norms with respect to the submultiplicativity operator. So let's take a look as to why this would be actually a less than or equal to sign. While we're at it, maybe I'll throw in for free why this doesn't necessarily have to be equal to. But let's start here with this sort of understanding with why is this a less than or equal to? Why is it that the norm of where c to the n sends an operator that is, again, thinking about what this norm is, this is the supremum over all vectors x inside of our vector space such that the norm of the vector x is equal to 1 of c to the n in norm times the vector x. So this is asking for this supremum here. And it is saying that that is less than or equal to the supremum of the norm of c to the x over all norm 1 vectors inside of the space, all raised to the n power. So this is the difference that is being asked for in this space. Notice where the n is in each of these operators. 1 is the norm of the operator c to the n, and 1 is the norm of the operator c, this stuff on the inside here, raised to the power of n. But in fact, we don't even need to use supremum for this stuff because we actually have a property that allows us to use this very efficiently, and it's the property of submultiplicativity. Remember that the way that this is defined is that if you have two operators being multiplied and you're taking this norm, then it is less than or equal to the product of the norms of the two operators, A times B. So what happens if you have n things being multiplied and put together here? What happens if I have the norm of c to the n that I want to take? Well, that's the norm of c times dot 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 times c n times n times. And what I can do is I can just step by step utilize this process and do this n minus 1 times instead. Take these norms and say, okay, well, by submultiplicativity, this is c times itself n minus 1 times one more copy of c, and I can separate out that last copy of c. And then I can do that again. Take c times itself n minus 2 times c times c, in terms of its norms. And then I can just keep doing this process until what I'm left with is c and norm times c and norm times dot 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 times c and norm, this being n copies still of the norm of c. And if I compile all of these into one value, then I'm looking at the norm of c raised to the power of n. So submultiplicativity gives me what I'm looking for very nicely. I just need to use it multiple times. We've had to do this sometimes with the triangle inequality, and this same sort of process works for multiplying copies of C with one another. So submultiplicity gives us there. As an example is where perhaps this sort of thing may not necessarily hold for equals to, because there are some operators in which you do get equals, but there are some operators in which you don't. This matrix right here, I could go through and show you, is a vector that gives you something. This is a matrix that is of norm 1. If I plug in this norm 1 vector inside of R2, what I end up getting out of it is also a norm 1 vector. I actually can't do any better than this. So the example here is that the norm of 0, 1, 0, 0 as a 2 by 2 matrix is norm 1. However, if I take the matrix 0, 0, 1, 0, this one, and I multiply it times itself, take a look at what I'm going to get. Multiplying through first row and first column is going to give me 0, 0. Then if I do first row, second column, that's 0 times 1 plus 1 times 0. That also gives me 0. And the bottom row, no matter how I multiply, is always going to give me 0 down here. And the norm of this matrix is going to be, since it's the 0 matrix, is going to be 0 as well. So you can see how I can get a strictly less than sign by looking at something here, which is the matrix 0, 1, 0, 0 quantity squared. That norm is less than or equal to the norm of the original matrix squared, which was just going to be 1. So there's an example that shows that these two don't necessarily have to be equal. And a good example for that one homework problem I was referencing from before, which had to do with submultiplicativity in homework 9. So any Banach space has a well-defined multiplication on it. We define I should say not Banach space. This should be a Banach algebra. And that is just by definition of what we have for an algebra, is that you can take two elements inside of a Banach algebra and define them in a multiplication. The types of Banach algebras that we're going to be focusing on in this class are just spaces of operators, the spaces we've been looking at, like L of V, whenever we talk about a Banach algebra. However, there are more examples of Banach algebras than these. We'll just be focusing on these because we want to keep our focuses on operators. So the following question becomes interesting once you have a multiplication operator. Does an element in a Banach algebra have a multiplicative inverse? So we have examples of what these things might look like in the space of 2 by 2 matrices. The matrix 0, -1, 1, 0 has a multiplicative inverse, which we have been calling A inverse. And it's the same A inverse process that we talked about from before. It's 1 over the determinant of the matrix times flip the elements on the diagonal and then take the negative versions of the numbers on the off diagonal. Or you can just check to see that when you multiply A times A inverse or A inverse times A, that what you end up getting here is the identity matrix either way. However, the matrix A equals 1, 0, 0, 0 does not have a multiplicative inverse. Many of you may come up naturally with the notion that the reason that this does not have a multiplicative inverse is that it does not have a determinant that is non-zero. The determinant is 0 for this matrix, and the way that we're taught in linear algebra is to say this means it cannot have an inverse. Let's be a little bit more detailed than that in saying why this does not have a multiplicative inverse. So here's 1, 0, 0, 0. And let's say that we are able to find a matrix A, B, C, D, that once we multiply it times the matrix 1, 0, 0, 0, like this, that we end up getting back to the identity matrix. This A, B, C, D would have to be the inverse of this matrix should it exist. So let's see if we can find the right values of what A, B, C, and D actually are, or if we get something that lines up into a contradiction. So let's try first taking a look at top row and top column. If we take a look and multiply these guys together, we're going to get taking a look at what this matrix would be by multiply top row, left column. Then we should get that 1 times A plus 0 times C is equal to 1. That tells us that A is equal to 1 for this matrix. Great. So we have a place to get started. That's always very good. Then we're going to have multiplying top row, right column, so top and right. If we multiply that way, we're going to get 1 times B plus 0 times D is equal to 0. So B has to be equal to 0. So we've got values of A and B now. What's going to happen if we multiply for the bottom right? I'll skip to bottom right for now. If we multiply the bottom row and this right column here, what I'm going to get is 0 times B plus 0 times D. Now that needs to be equal to the bottom right corner of this matrix. That needs to be equal to 1. But the left-hand side is equal to 0, and that cannot equal to 1. So this shows us that as we go through and assume, okay, well, if we did have an inverse, it would have to be of the form A, B, C, D. It turns out that because the bottom row of our matrix has a 0 row, we cannot have a multiplicative inverse because we would still need to have a 1 somewhere in that bottom row for this to be able to work. Otherwise, we end up getting to an equation when we multiply out our matrices that we get that 0 is equal to 1, and that gives us a contradiction. That notion, by the way, is exactly what the determinant is all about. The determinant of a matrix tells you that after row reduction, you either do have a 0 row, in which the determinant yields 0, or after row reduction, you cannot get a 0 row, in which case the determinant is non-zero. So that's what the determinant tells you. That's why we end up taking determinants of matrices to determine whether they are invertible or not. So in general, we could go through and find inverses for spaces that perhaps are not even the same. We talk a little bit about how this works in the space of matrices, because when you're trying to find some sort of invertible linear operator, to be clear, then what you're looking for is something that goes from one space to this other space, and they have to map bases, excuse me. They have to map a basis of the space of Rn to another basis, which is similarly linearly independent when you map it through to this other vector space. It turns out that in order for your linear operator to be bijective, then your dimensions have to be of the same size, and hence Rn, the space that you would map Rn to, has to be at least isomorphic in same structure as the space of Rn. Maybe you could find a linear operator that is invertible from the space of Rn to the space of polynomials of degree at most n-1, because that also has a dimension of n, but that's all that you could do. You don't get an ability to really do much else there. In the world of infinite dimensional norm vector spaces, on the other hand, it is very possible that you are able to find an inverse between two different vector spaces, just because everything is infinite dimensional. We can't count dimension as a way to determine whether or not there is a way to calculate an inverse or not for any two operators, or for any given operator. So again, just to be clear, when we are talking about inverses here, we are saying that we are looking at them in the same way of like multiplying using composition, that if you have normed vector spaces U, V, and W, and two operators that map you into the interloping spaces, then you can define an operator, say BA in this space, to be A times the vector X, which maps you from a norm vector space from U to V. If X, for example, is a vector inside of U, then A times X would be a vector inside of V, as that's what A does. And then now that this vector is inside of V, B times AX will be a vector that is inside of W. So this BA will itself be a operator that takes you from a space beginning at U and ending at W. Notice that with this sort of definition of BA, there's no need for us to be able to commute. Just like with matrices, the reason that matrices do not have to commute is that sometimes the way that you define the linear operation dictates that when you flip around the two matrices, you may not even get something that is well defined. And even if it is, it does not necessarily need to hold true that BA is equal to AB. The same thing holds for operators. You can take two operators and multiply them in separate orders and get different operators from the composition. So we're going to make sure that we're avoiding that when we talk about BA versus AB. It's very possible that switching those two orders gives us something that is not exactly the same. So one example of that is that if you just take a linear operator that goes from between two vector spaces like V and W, we will say a bounded linear operator between two vector spaces is invertible if there exists a bounded linear operator that goes backwards from the two spaces, such that B times A is the identity matrix for the vector space V, as this BA would be something that goes from V to V, and that AB is the identity operator as it exists on the vector space W, as AB would be an operator that goes from the vector space W to itself. The operator B is the inverse operator of A and is denoted by A inverse. We will see some examples in our homework of some examples of operators that don't have inverses and what those sorts of things might look like. We will see some examples as well of some things that look like they have inverses, but where the inverse itself is not bounded. Here, we're calling B A inverse. So when we say we need this inverse to B to exist, and whenever we start trying to call it A inverse, we are going to ask that that inverse is bounded. Now, that may seem like it's a little bit of a strange ask because A itself is bounded already. We say a bounded linear operator A is invertible. So we start with a bounded linear operator A. If you're going to invert A, doesn't the inverse also have to be bounded? That ends up not necessarily being true. That if you try and invert a bounded operator, it's very possible that what you get is not bounded. So we'll see an example of that here in the next slide. But let me try and go ahead and give you an example of something that works the whole way through with this definition. What's a good example? They don't have that at all. I love the idea, but oh, it didn't. It didn't pause. I'll have to cut that then. All right. 3, 2, 1. So let's take a look at one of these examples. I'm going to do one that does go from one space to itself, just to kind of get us some idea of what these sorts of operators might look like. Let's say that I take an operator that goes from the continuous functions on the real numbers to itself. And the way that I'm going to define it is this. I'm going to take T of f. So here, f is going to be a function that goes from R to R. This is some function. I could plug in a real number, x, and I could get out another number, y, out of that. And the way that I'm going to define TF, this operator here, is that if I plug in a value x inside of the function that TF is, as that gives me another function, a continuous function out of the real numbers, and I'm going to connect that back to the original function f that I got and gets the function x plus, or gets the value x plus 1 from that function. So here's what I mean by that. Let's say that you start with a function f of x is equal to x squared. Then TF, mapping a function that is continuous function on the reals, will have to also give me a continuous function on the reals. And here's how I'm going to define that function. TF of x is going to be just f of x plus 1, which would give me x plus 1 quantity squared. Another continuous function. What did it do? It kind of took the graph of the function f of x equals x squared, and it shifted it to the left by a unit of 1. That's what this operator T does to the graphs of these functions. It shifts it over to the left by 1. Now, this is a well-defined operator, and indeed, it is linear. However, is it invertible is another question. Well, T we described geometrically in a way that will help us understand why it might be invertible. We could also maybe see it algebraically just from looking at this, what we might need to do to invert the operator that takes a function and maps any value of that function to f of x plus 1 instead of f of x. But if we look at this as a graph being shifted to the left by 1, then the inverse function, whatever it's going to have to do, is going to have to send us back to the original function. So if T maps our function to the left by 1, what should our inverse function S do? Well, it should take this function and it should shift it to the right by 1. We should be taking a look at how functions map us to f of x minus 1 for the y value. Remember that in order for something to be invertible, we are asking that when you take a function T inverse T of F, which is take the function, map it through T first, then map the resulting function through T inverse, we want to be back to the original function. And we can check that with this one. We can start by taking a look at what TF does to the point X. That's going to give us, by definition, this is F of X plus 1. And then do what T inverse does, which is takes us to F of X plus 1 minus 1, which is just going to be equal to F of X. And this is an example of an inverse of this function. We can also, and do have to, make sure that it also works the other way. If you have T times T inverse of F, does this also invert? If it doesn't, then we don't have an inverse. That is important. If this inverse does not work one way or another, then we end up getting something that is not an inverse. There are notions, by the way, of something called a right inverse or a left inverse that do exist. It's possible for something to not be invertible because one of these T inverse T or one of these TT inverses do not work. They do not give us the inverse that we're looking for. So keep that in mind, especially as you go through your homework, that sometimes you can get an inverse that exists one way, but does not exist another way. But this does work both ways. So this is an example of an inverse. If you just take any continuous function on the real numbers and map it through so that the T shifts your graph to the left by 1, then you can shift it back to the right by 1 and get back to your same function. This is an example of an inverse operator. Inverse operators work very much like matrices in that if you have two invertible operators and you are able to map them together, then you can do the same thing to BA. BA is also invertible, and its inverse is equal to A inverse times B inverse. Note the switch in order. It'd be neat to go through and ensure you know why that actually is the way that it works. Check that a little bit with some of the things and tools that you've been learning from this class. But I want to show you this example of an operator that is bounded, but that when you take its inverse, it is not bounded. Let's go back to the space of little L infinity. And let's take something that takes our standard basis vectors from little L infinity. Recall, this is the vector that has a 1 in the spot and 0 elsewhere. So E sub I, for example, has a 1 in the ith spot and 0s elsewhere. That is a bounded sequence of norm 1. And let's say that what this operator does to the basis vector, E sub I, is that it divides that vector by n. Oops, I think I should have said something else here. My bad. Let me fix that. Let's call these T sub n instead. This should help it make sense, actually. There we go. That will make a lot more sense. I will use T times the vector E sub n instead. And say if you are trying to map the nth basis vector, take it to be 1 over n, where n is the index of that basis vector, times the vector E sub n. So when I say extended linearly, just a reminder of what that means is if I take a sequence like 1, 1, 1, 1, and so on and so forth, then because this operator, or this sequence here, is a sum of basis vectors, this is the sum of the sequence that is 1 in the first spot and 0 elsewhere, plus the sequence that is 1 in the second spot and 0 elsewhere. If this was like a 2, for example, in the fourth spot, then I would write 2 times e to the fourth and 0s elsewhere. And when I say to extend it linearly, I mean go ahead and make it what you think it should be, because all of these are just additions of what they should be. For example, we could map this to be linear by breaking up the sum and bringing multiples outside. This is TE1 plus TE2 plus TE3 plus 2 times TE to the 4, and so on and so forth. And we can just take whatever those sequences are and map them and put them together. This will still be the sequence 1, 0, 0. TE2 is a 1 in the second position, but I'm also going to be dividing it by its index. So that index is 2. So that's going to be 1, 1, 0, 1 half, 0, 0 as this sequence. Then this next one is going to be 0, 0, 1/3, 0. And then plus 0, 0, 0, 2/4, because of the 2 there, 0. And then I can add up all of those sequences together to give me what this ends up being. So something like this for this sequence. So when I say extended linearly, I mean break it up to make T a linear transformation. This is a bijective map. Each basis element is not getting moved around anywhere. It's just getting shrunk by a factor of n. You're still going to be able to get injectivity from that as well as surjectivity, and you can check that if you would like. It can also be shown that the norm of this operator is equal to 1. Whenever you map a sequence whose first component is not 0, through this map, what you're going to get is that the supremum of the sequence is still going to be equal to 1 for that value. So for example, just mapping through 1, 0, 0 through the sequence, t of this sequence is still going to be itself. And because this is something which has an upper bound of 1, the norm of this sequence is equal to 1. This is the exact same sequence. So the norm of t has to be at least equal to 1, and indeed the norm of t is actually equal to 1, because the other sequence elements, whatever the operator t is doing to those basis elements, is actually shrinking them instead of trying to grow them at all. So you can see that it's because norm is measuring how much bigger or smaller a sequence can become, that the largest that this t can do to a sequence happens in the first component, and it's just going to keep it the same. The inverse map of t can be shown to be the thing that, instead of shrinking everything by a factor of n, kind of like what we did on the previous slide, it actually grows it by a factor of n. It just flips everything in that. Now, what is this operator s going to do to this space? What it's going to do is it's going to take something like 1, 2, 3, 0, 0, 0, and what it's going to do is it's going to take 1, and it's just going to map it 1 to itself. That's the index times its of 1 times the number that's in there. What's it going to do to the number 2? It's going to take 2 and multiply it times its index, which is the second position. So it's going to give me 4. Then what's it going to do to 3? 3 is going to get 3 times its index, which is going to give me 9. And the zeros are still going to stick around. So S, what it does is it, instead of shrinking down further and further elements of the sequence, because it's trying to undo what t is doing, which is dividing by n, it is going to multiply by n instead to get everything back into equilibrium with what the original vectors may have been that you plugged into the operator t. This is also a linear map, but it ends up not being bounded. You can see that what this sequence does is it blows up numbers. The largest bound of this sequence is 3, and the least upper bound of this sequence is 9. That is already something that is tripling the size of the norm, and that's still with a lot of zeros over at the end there. If we kept going with these sequences and even just looked at a sequence like S of 1, 1, 1, 1, and so on and so forth, taking a look at a sequence like this, well, the sequence element that we end up getting for something like this is going to keep growing and growing and growing and growing as long as you have ones inside of that sequence. S does not work very neatly here in this space. In fact, S does not even keep any vectors that you had that were bounded in little L infinity inside of that space. Multiplying times n, this is an unbounded sequence now. This is the sequence of the natural numbers, and it's going off toward infinity. This is why we want to avoid these types of contexts in the types of operators we look at. And so we don't call something invertible unless the inverse is also bounded. Here, the inverse S ends up blowing up numbers too much for them to even have a norm. You can see here how I go through and describe that, which is that if you take a look at the sequence of norm 1 elements, you can get norms that are as big as you would like them to be, as big as n is allowed to be, and n is allowed to grow toward infinity. So using our definition of operator norm, this can grow to be as large as it wants to be. So when we define an inverse operator, we ask for the inverse to also be bounded because of examples like this. Let's keep going with some of these ideas with also taking a look at boundedness. I didn't need this part inside of this process, so I don't need this in there. So let's assume that U and V are normed spaces and that A, going from U to V, is a surjective bounded linear operator. Let's further assume that there is a real constant such that the norm of A times the vector U is greater than or equal to C times the vector U's norm for all vectors U inside of our domain vector space. Now let's show that A is invertible. So to show something is invertible is to say that not only does it have an inverse, but that it also has to be bounded as an inverse. We automatically know from one of our propositions 2 slides ago that if you have something that is like there is an inverse map, it's automatically linear. If A is linear, A inverse is going to be linear. So we don't have to check that. But we do need to check and make sure that A inverse is bounded in this whole process. Let's take a look at what we have to use and start trying to reason through why something like this might be true. If I take a look at this inequality here, it looks very similar to something that I've seen before. If I took this sign of greater than or equal to and switched it with a less than or equal to, this looks a lot like one of our definitions of the operator norm of A. In particular, C would be, if you took the infimum of all of those values of C that could possibly exist for this inequality, C would be what we call the operator norm of the operator A. But this is greater than or equal to. This is a little bit different. It says that whenever you map a matrix, a vector U through an operator A, then what you get is actually bounded below in norm by C times the norm of the vector that you plugged in there. So let's see if we can figure out why that means that this is an invertible matrix. Now, we're going to start by just doing invertible map. And we're going to deal with the boundedness component later on. So we'll break this up into two parts. First thing we're going to do is just go back to week one. Week one, how do we show that something is invertible? It would need to be injective and surjective, right? We already have that this is a surjective map. So is A an invertible map? We know it is surjective. So what do we need to show now? Need to show that it is injective. Recall what injective means. It says that if you have two distinct vectors inside of your domain space, then they have to map to two distinct vectors inside of your codomain. That is, let's say that you have vectors U1 not equal to U2 inside of your domain space, which is capital U for us. Let U1 be not equal to U2 inside of this space. To show injective, we want to show that if you map A U1, then that's not going to be equal to A times U2. So let's see if we can do that using this inequality. Well, we could start by looking at what this is as a single vector. We see here that the only thing that's involved is a single vector U, and we can form addition and subtraction of vectors inside of a vector space. That is well defined. So if I took U1 not equal to U2 and tried to consider them as a single vector, one way that I might do that is try subtracting one vector from another and look at the single vector U1 minus U2, which is not the zero vector then. This is coming from subtracting U2 from both sides. Well, if this is true, I want to figure out something about what I have over here. Maybe I would like to try and see if A U1 minus U2 is also not equal to the zero vector. Maybe that's something that I could try to do this. How did I do that? I subtracted A U2 from both sides and used the fact that A breaks up and also combines additions and sums. So there's a little in-between step that I did here, which is A U1 minus A U2 cannot be equal to the zero vector. And I can also factor out, if you will, by this operator A. Now I have something that looks very similar to what I have here in my inequality. I know that U1 minus U2 is not equal to 0, and this is what I want to show. So I still don't have this part. You can imagine me again going through my proof column with a start column and an end column, and I'm figuring out how I would like to connect things in the middle here. I have that U1 minus U2 is not equal to the zero vector. I also know, just from this fact alone and the inequality that I'm given, that if I look at A times U1 minus U2 as a vector, and I'll put these together as one vector like this, that the norm of this is going to be greater than or equal to C times the norm of U1 minus U2. So this is by our inequality. That the norm of A times the vector U1 minus U2 is greater than C times the norm of U1 minus U2. What I know about U1 minus U2 is that this is not equal to 0. What that means to me is that this norm is not equal to 0, which means it has to be greater than 0. Putting this together with this tells me that the norm of A U1 minus U2 is strictly greater than 0, which we know can only happen with, because of the definition of a norm, whenever you look at A U1 minus U2 and what you have is not the zero vector. because the only time that you can get a norm equal to 0 is if you have the 0 vector, and vice versa. If you have the 0 vector in there, its norm has to be equal to 0. So this is coming from the definition of the norm. Well, now we just get to follow everything all the way back, which eventually is going to be able to say AU1 minus AU2 is not equal to the 0 vector, which means that AU1 is not equal to AU2. And this is the definition of injectivity. So this showed us that we actually do have an injective map just from this inequality and using the definition of it. So A is bijective, which means a linear map, A inverse, exists. Is A inverse bounded? Is now our next step. We now want to show if A inverse is bounded. So let's take a look at this inequality real quick. I have an inequality that involves the operator A. Could I somehow get A inverse to be involved in here? Let's think about how we could do that. So in order to show if A inverse is bounded, we want to show that essentially, let's say that you take a vector X, or I'll say V, that's inside of our codomain space, such that the norm of V is equal to 1. We want to show that the norm of A times the vector V is bounded above. So for any arbitrary vector that is inside of our space, which is now our codomain space, because we're going backwards now, A inverse goes from V to U instead of from U to V. We want to now show that the norm of A times V is bounded above. So this is for A inverse, which is flipping our two directions here. So let's see if that's something that we could do. I guess I should have said A inverse times V. I forgot about that part. There we go. So there's A inverse times V. Well, recall that A inverse V is equal to a vector U whenever the way that we define inverse maps is that the vector V itself is equal to A times the vector U. So we want to show something about what this will look like. Let's see what we can do here. We do know something about A times the vector U, I suppose. We do know that A times the vector U is going to be less than or equal to C times the vector U. This is by our inequality again. So we know that if you have something of the form A times U, this is just me using that same inequality that we had from above here, then I'll have that that's greater than or equal to C times the vector U. But take a look at what I have equal to the vector U. What I have there is, this is the vector of A inverse V. So this is C times A inverse V. So this is just subbing in what I know U to be equal to, which is what this is right here, A inverse times V. I also know A times U is equal to something in terms of the vector V, and take a look at what happens when I plug in both of those things. I get that V is greater than or equal to C times A inverse times the vector V. Am I close to getting a bound above for the norm of A inverse V? Well, I have something that could bound above C times A inverse V in norm. So the last thing that I need to do is just divide both sides in order to get what I'm looking for. And I'll divide both sides by C. So this is 1 over C times the norm of vector V. And this inequality right here is telling me that I have that A inverse B is bounded above. So by definition, A inverse V, A inverse is bounded. So it is an inverse, and that gives me what I'm looking for. So we can use some of the things we used all the way back in week 1 together. So the notions of injectivity together with the boundedness that we've been learning about these last couple of weeks to put those things together and start working through some pretty neat arguments to see when things are invertible and when things are not, like in this example here. Let's do one last thing before we go. And this is just something neat that I saw in the reading that I wanted to highlight here. This is something I believe that they call the, what do they call it? The Neumann series. The thing that comes after this, the Banach lemma, whatever that is, I don't really fool with that much stuff, and I don't think we're going to be going in that direction. So you don't have to worry too much about that particular section. But looking at the Neumann series, I thought was very interesting because the Neumann series connects us to normal series as well. So looking at power series, like the power series as n goes from 0 to infinity of x to the n, we have used that the series converges to 1 over the value of 1 minus x whenever the norm of x is less than 1. An interesting corollary arises that does a couple of things. One is it says that the corresponding notion of this series works in operators. That is, if I went through and I looked at 1 over the operator, which is the identity minus the matrix A, that is, if I looked at I minus A inverse, could I write that as, subbing out A for x, could I write this as the sum as n goes from 0 to infinity of A to the n whenever the norm of A is less than 1? Notice how we've just 1 for 1 subbed out everything. That the sum as n goes from 0 to infinity of x to the n has become the sum as n goes from 0 to infinity of A to the n. So x is getting subbed out for A. Then we have 1 over 1 minus x, when by 1 here, we are really meaning the identity matrix, because that's what we are looking at with this thing, is that I is like 1 inside of these spaces. And instead of 1 over, oops, I should write that a little clearer. Instead of saying 1 over to talk about the reciprocal, we are using the notion of inverse. And then the notion of absolute value is subbed out for the notion of a norm, because indeed the norm on real numbers is just the absolute value. So we're just switching this out and making it a bit more general. Each of these concepts connects to another concept we've been using for geometric series. And an interesting corollary arises. Is it true that this sum exists? And the answer is yes, it absolutely does. Whenever you have a complete norm space, that is when you're looking on a Banach space, such that and you have an operator with a norm strictly less than 1, then the operator I minus A is invertible. And in fact, its inverse can be calculated as the infinite sum of operators of the form as n goes from 0 to infinity of A to the n. It's an interesting thing to think about what these sorts of A to the n operators might look like. I'll give a straightforward example from looking at matrices. And by straightforward, I typically like using diagonal matrices to kind of help out with this. You might ask the question, what happens if I take this matrix and raise it to the nth power? It can be shown that what I end up getting is something like this. This is what it means to raise a matrix to the nth power. Well, something else that I can do with these matrices, because they are going to be so small, that is, because the norm of the original matrix that I was using was less than 1, I can sum each of these matrices together and get another matrix out on top of that. This matrix, 1 over 2 to the n, 0, 0, 1 over 4 to the n, if I go through and sum all of these matrices together, I'm going to get something like 1, 0, 0, and 4/3. Actually, I believe it's 2 up here. Check and make sure that that's true. And then we check my 4/3 again right down here. So I'm going to get what? 1 plus 1/4 plus so on and so forth. So that should be equal to what? 1 over 1 minus 1/4. Just checking all the math here to make sure I get it right. Okay, yes, I was right. I had to go back and check and triple check all of the formulas. But where that's coming from is that each power is 1/4 of the original one. So the formula that I get for this value is 1 over 1 minus 4. So this is 1 over 3/4. So this is 4/3. And this matrix is the inverse of the identity matrix 1, 0, 0, 1 minus the matrix that I started with 1/2, 0, 0, 1/4. This is what we're claiming here. Subtract these two matrices, and what you end up getting is 1/2, 0, 0, 3/4. Take a look at these two matrices and notice these two are inverses of each other. Just take a look at the diagonal entries. 2 and 1/2, multiplicative inverses. 4/3 and 3/4, multiplicative inverses. This is what we're saying works at any dimension as well as an infinite dimension with this proposition, where the convergence here is with respect to the operator norm. Let's just walk through this proof very quickly as we kind of talk about it a bit. The whole idea here is to use completeness to turn things into working in Cauchy sequences and Cauchy sums instead of everything else. In fact, it ends up being absolutely Cauchy. We can see here that if you take two sums of this form where you look at partial sums, where you cap them off at a specific point and look at their difference at different points inside of the sequence, then all you're looking at is sums going from, say, some n+1th point to an mth point of the norms of A sub n, which you know are going to grow to be very small because of our first example here in this video lecture. So you can break this up to be the sum of the norms of A to the n. And if you know what this is, this calculation comes from what happens if you start a geometric series at a point that is not equal to just 1 plus for its first partial sum, that you can just multiply everything times the first thing that you would be plugging in. So this formula comes from the notion of a geometric series where first partial sum is not equal to 1. So that's where that formula comes from. And then if you take a look at what happens if you continue to push the cutoff points on and on, as you would with a Cauchy sequence, this numerator is going to grow smaller and smaller because of how you started. The norm of the matrix or the operator that you're using has to be strictly less than 1. So this value is going to go towards 0, which means that this whole value is going to go towards 0. The last thing that we just need to go through and check is to see that the series that you get indeed does converge to the identity matrix. So you can see here in this bottom part that I'm going to take I minus A. I'm going to multiply it times the partial sums of this inverse. I minus A is the thing that we're inverting. S sub n is the thing that's supposed to be the inverse of it. So the inverse for these two things, if these are supposed to be invertible, then if I'm just taking partial sums so that things could converge, these should be converging to the identity matrix. This is the identity matrix here. You can see that I wrote it as 1 to begin with. And we can check that indeed that's exactly what happens. We get a telescoping sum of some copies of the operator A to the n, which start at n equals 0, which give me the identity matrix, and end at capital N plus 1, which gives me this minus A to the n plus 1. If I subtract those two values, then I get something that is bounded above by the norm of A raised to the power of n plus 1, which tells me that this convergence is going towards 0. So S sub n has to be the thing that is the inverse of this matrix. It's a neat little proof to see that we can adapt many of the things that we use for partial sums in the world of operators as well. But that'll do it for us today. We've been seeing some neat things here with inverse operators today and getting a little bit familiar with how these things work in extending from the world of matrices to the world of operators. But thank you so much. Have a wonderful day.